Thanks. So I'll talk about thermal stability and universal adiabatic computation, and really what it's about is doing universal quantum computation in a time-independent thermal state of a local Hamiltonian. This is still a work in progress, but everything I'll tell you about today is pretty solid, and it's also joint work with Thomas Joachim O'Connor, who is a fellow postdoc at Caltech, and John Preskill. So to start with, we have the local Hamiltonian problem, which tells us that it's QMA complete to decide the ground state energy of a local Hamiltonian up to inverse polynomial precision. And the construction in this result that shows the QMA hardness involves embedding a time-dependent universal quantum computation. So here's the ordinary time-dependent view where you apply some gates and have a state that evolves with time. And turning this into a time-independent superposition where the computational state at each time step is entangled with this additional ancillary register, which is called the clock or the time register. And so you have this time-dependent superposition. So you can think of, if you were to measure the time register of this state, you could collapse it onto the final time with some probability 1 over capital T. And then you can measure the output of the computation. So if you can produce this ground state, then you can read the result of your computation. And so the question I'm going to address today is whether this complexity that we know about for ground states of local Hamiltonians can persist at finite temperature. And a topic that's closely related to this ground state complexity is the fact that these states, which are called history states, are used to show that ideal noiseless adiabatic computation can be universal. So adiabatic computation, think of it as the model where you are in the instantaneous ground state of a slowly evolving Hamiltonian, such that the ground state is separated from the rest of the spectrum by some spectral gap that kind of governs how quickly you can change the Hamiltonian while remaining in that instantaneous ground state. And so these kinds of history states are used in the existing proof that adiabatic computation can be universal, but this sort of assumes that the adiabatic computation is ideal and noiseless. So while we have a well-developed theory of fault tolerance for the circuit model, it has not been adapted to the adiabatic model, which is something I hope to address today, although we have to be careful. There are many things involved in addressing that, and one of the first ones is what kind of noise model do you want to consider? So we'll talk about those issues. So today what I'm going to do is I'm going to combine these history states with self-correcting topological quantum memories or other fault-tolerant schemes, and use this to show that universal quantum computation can be encoded in the metastable Gibbs state of a local Hamiltonian. And here metastable means that the lifetime of sort of this computational state might be exponentially long, whereas we hope, or whereas you would like to prepare the state in polynomial time, let's say. So yeah, we'll talk about metastability and how we might want to go beyond that at the end to answer some of these complexity questions about the true equilibrium Gibbs state. It's a little easier to analyze this metastable case. So there's kind of a lot of background to explain this. First I'll tell you about quantum ground state computing and the standard results on universal adiabatic computation. And then we have to describe something where you don't have a global time register, but you assign sort of a clock register to each of the individual qubits in your computation. That was worked out. And then we'll talk about self-correcting memories in the classical and quantum case. And then I'll start telling you about some of the new stuff. So the fact that we want to have the circuit Hamiltonian, so the fact that the Hamiltonian must be k-local means that we have to take advantage of transversal operations. Those are essential. These transversal operations are going to demand that we have this kind of local clock construction, and we're also going to, so another ingredient involved in the construction is that we're going to include the classical post-processing that you would normally think of. So normally in fault tolerance, you might have some quantum computing architecture and you might measure check operators for your quantum code and then do some classical post-processing on the side. But really, that classical post-processing is part of the quantum world, and we can consider a larger picture where everything is unitary, and the classical post-processing computer is also embedded into the quantum system. So that's going to be a part of our quantum Hamiltonian. So then we'll talk about some of the issues that come up when you start to take this space-time view of self-correction or topological quantum memories. And one thing to sort of keep in mind, the inspiration here is we're going to take a fault-tolerant quantum computing laboratory, which is to say the quantum computer and the classical post-processor, and take this four-dimensional, everything is unitary, coherent point of view, and put all of this into a history state. Well, okay. And so then I'll go into some of the analysis, so if you're familiar with, and I'll explain what happens in universal adiabatic computation, the standard analysis, there's sort of this global rotation that takes you from a complicated system to a relatively easy system where everything is static. And that global rotation, we get a lot of mileage out of that in this construction, and it actually allows us to analyze the thermal state and its dynamics. Then I'll summarize. Yeah?
So are you concluding from this that adiabatic quantum computation is universal even if there's noise? Is that?
That's essentially the goal. So we have to talk about exactly what kind of noise we want to address, and I'm open to suggestions for what more should be included. But let's think of low temperature, so below some critical temperature that is system size independent, and we want maybe weak coupling with a bath, although maybe that can be improved to strong coupling. So I'll say something about the Davies-Master equation in the thermal analysis. And the other thing you want to consider is some possible errors in your local Hamiltonian terms. So in real world quantum annealing, this is actually the predominant form of noise. So I'll analyze some parts of the stability, although some of the discussions that came up yesterday, sort of if you remember the point about a pencil standing on its tip, that provided me a new goalpost that I need to adapt to.
Goalpost standing on its tip.
Exactly. So I hadn't quite incorporated that yet, but I think that can be done as well. Right. Yeah, so those are the two types of noise, and then the conclusion will be, and then you also have to discuss exactly what you mean about adiabatic computation when you're at non-zero temperature, right? Because, so you have to use an open system adiabatic theorem if you really want to prove efficient preparation. And I won't say too much in my slides about efficient preparation, although I can discuss it more on the board or so, if there's interest in how we can lower bound the spectral gap of this complicated construction I'm going to describe. So yeah, what do we mean by adiabatic computation at non-zero temperature? Well, you should be in the steady state of the Hamiltonian, or at least the metastable steady state. And I think so, given all those sort of caveats. And then also there's another issue that comes up in adiabatic computation where it's not always the global spectral gap, but the spectral gap within a subspace that can guarantee you succeed. So now if you sort of allow all these extensions and generalizations and you go against this noise model, then yes, our construction seems to work to achieve universal quantum computation against noise. So highly entangled states look maximally mixed with respect to local operators. So the fundamental problem if you want to do quantum computation in the ground state is you can't just lay out all the time steps of your computation on distinct sets of physical qubits like you would with a classical sort of Cook-Levin tableau that records the history of your computation. So the question is, how do you check quantum computations with local Hamiltonian? So this problem was solved by Kitaev by repurposing an idea from Feynman, which is that I described on the opening slide, which is that you want to entangle the time steps of the computation with this additional register. So now we have n qubits, and you have some time register, and so you don't have a number of qubits equal to n times the total number of time steps. You're really leveraging this entanglement because this is what's going to allow you to check the computation locally. So checking the computation locally means that we have a local Hamiltonian for which this is the frustration-free ground state. So what this Hamiltonian looks like is this. So there's a term that forces the correct state on the input step, but the main part to look at here is the propagation term. So what the propagation term checks is that as you go from t-1 to t, you apply this unitary gate that you are meant to apply at time t, and then you have the Hermitian conjugate of this, and this part just sort of normalizes everything into an overall projector. So that's not so important, but the point is that you can think of this clock register as sort of hopping along with the gates being applied to the quantum system. So the input term acts at the clock. It says that the clock is at time 0, and you're sort of projecting out any possibility of being of your qubits being in the 1 state. So the low energy state has all of the qubits at the initial time step in the 0 state. That's just without loss of generality, because you can always feed in the same input and just adjust the gates to do the computation you want. One more thing to mention, although I won't do much detail about it, is just that this clock register has to go up to some polynomial total time. So if you actually want to break that down locally, there's this construction worked out where you have a domain wall clock where you represent the time variable in unary notation, just in terms of qubits. And so updating the clock just sort of means moving this domain wall to the right.
So the kind of dimension of your Hilbert space depends on the time, or on the amount of time that the computation runs.
Yeah, that's right. That's right. So yeah, this unary clock. So we really only want to do computation for a polynomial total amount of time.
And the unary clock keeps the action on the clock register local.
Yes, exactly. So now when we do this update from t-1 to t, you're going to look for the state 100, and you're going to update it to 110. Okay. Okay, so how do you analyze this construction? Well, it turns out that this propagation part of the Hamiltonian is unitarily equivalent to a particle hopping on a line. And so to see that, you define this unitary W, which sort of acts conditionally at each time and performs the circuit up to that time. And when you conjugate the Hamiltonian with this unitary, what you'll find if you calculate it is that you're left with an identity on the time register, and all that's sort of left of the Hamiltonian, so there's implicit identities here, right? And all you're left with is this Hamiltonian that describes a particle hopping on a line. So you went from this point of view where your history state records the computation at every time step, but you rotate away the computation so that you're left with sort of a static picture where you're just repeating the same input state at every time step in this rotated frame. And so if you have a particle hopping on a line, well, that's a system that we understand very well. It's a free particle. And you can think of it as a diffusive random walk. So, you know, the mixing time, if you like, to equilibrate to the uniform distribution on this line is going to be like t squared, capital T, the total number of time steps, and the spectral gap is like 1 over t squared. Okay, so universal adiabatic computation. So the general idea behind any ideal ground state adiabatic computation is that you want to initialize the system into an easily prepared ground state, and then you want to linearly interpolate to some final Hamiltonian which can actually, whose ground state encodes the computation of interest or solves the problem you're trying to solve. And so the adiabatic theorem of quantum mechanics, well, there are various adiabatic theorems. Let's just sort of take this runtime estimate. So they all scale polynomially in the norm of the Hamiltonian, which is like the number of qubits, and the inverse spectral gap. Yes?
Is the linear interpolation important, or aren't there reasons to sometimes take alternate paths to avoid promise paths?
Yeah, absolutely. Yeah, you can sometimes get a speed up by optimizing the path, and yeah, any sort of continuous path in the space of Hamiltonians would suffice as long as they stay local.
I just want to make sure it wasn't important for what you're about to talk about.
No, it's not. It's not crucial. Yeah. Okay, so if you want to do sort of the standard universal adiabatic computation, your final Hamiltonian is actually this initial part plus this propagation part, because you want the ground state to be the correct history state, and your initial Hamiltonian is just what I called H init on that slide. So it's just this piece. So you interpolate between just this piece, and then you add this entire thing, right? This piece plus this piece. And you can use a sort of monotonicity argument to show that the minimum spectral gap occurs as your adiabatic parameter S approaches 1. And so we just sort of saw in the previous slide about the hopping particle that the spectral gap is inverse polynomial in the total runtime. So according to these sort of adiabatic theorems, the overall runtime is polynomial in N and T. And I won't actually make use of this, but so in case this Hamiltonian looks really abstract, you can put it into more of a familiar form by using these perturbative gadgets that have been worked out, so that you can sort of implement all these terms using a two-local Hamiltonian, maybe with a complicated geometry of connectivity. But you know, you can essentially express this Hamiltonian effectively in terms of two-body Pauli operators. I haven't even begun to think about how one would apply perturbative gadgets to the thermally stable construction I'm going to describe, because then you would probably throw out the thermal stability. These perturbative gadgets are relatively fragile. Okay, so now I'll talk about an